Hello everyone, it's Mr. Spinelli, and today we're going to talk about solving quadratic equations using the quadratic formula. So on this slide we see a generic equation. So A, B, and C could be any number in the world you can possibly think of. 5, 27, -32, pi, e, any number that has a value. And the so-called quadratic formula, which you see written here, gives you the solutions. And I say solutions a little differently because there could be zero solutions. That is, there's no real solution. There could be one solution, or there could be two solutions. So the key thing to notice in this formula is that it has a plus or minus. So all we need to do in order to use the quadratic formula is make sure that our equation is in the form ax squared plus bx plus c equals 0, which is standard form. So let's take a look at some examples and we'll get those calculators going. So in this, I note that a equals 5, b equals -7, and c equals -11. So now all I need to do is apply the quadratic formula. So then x is equal to -b, so I'm going to have a -7 plus or minus the square root of b squared, so -7 squared, minus 4ac. A is 5, c is -11. And then all of this gets divided by 2a. So now this is a simple matter of plugging things into my calculator. Now I like to start on the inside of the square root. This is known as the discriminant. Okay, so this is the discriminant. And it's going to give me some information. And it's just nice to plug this into my calculator so I don't have errors. So I'm going to square the -7. And then multiply 4 times 5 times -11 and subtract that result from 49. And you should get 269. Now this -7 at the beginning is simply 7. So I have 7 plus or minus the square root of 269. And then 2 times 5 in the denominator is simply 10. Now this is my exact answer. I know that I have a solution of 7 plus the square root of 269 all over 10, and I have an answer of 7 minus the square root of 269 all over 10. Those are exact. Now I can type each of those in my calculator, and the first one gives me 8.640 to the nearest thousandth, and then 5.360 for the second one. Again, those are rounded to the nearest thousand. But I prefer this answer right here because it contains both answers at once and they're exact. So all I did was plug into my formula, which again is -b plus or minus the square root of b squared minus 4ac all over 2a. So let's try another example. Now in this one, I notice that there's no b value. I don't have anything in front of the x. Remember, it's got to be in standard form, ax squared plus bx plus c. So my a value is 5, my c value is -17, and my b value is 0. So my formula says that x equals -b, so just -0, plus or minus the square root of b squared minus 4 a, c, all of that's under the square root, and all of that is divided by 2a. Now notice I use parentheses because this is exactly how I would type it in my calculator. So if I type this discriminant, the inside of the square root, if I type all that in my calculator, I should get 340. So I get plus or minus the square root of 340 all over 10, because I really have a 0 in front of this, but I don't need to write that. So then if I type this in my calculator, again, this is my exact answer. Some teachers may have you simplify this a bit, but that's beyond the point. You get x equals plus or minus 1.844, rounded to the nearest thousandth. Okay, so I have two answers. I have a positive 1.844 and a negative 1.844. So notice the similarity between these two problems, and we'll see what happens with maybe a different one. All right, same thing here. I've got my A, my B, and my C. I'm going to plug into the formula. So I've got negative B plus or minus the square root of B squared minus 4AC. You can see I kind of dropped some of my parentheses because I didn't have as many negatives going on. All over 2A. So if I compute the discriminant, the thing inside the square root, I get negative 167. This is all divided by 14. Now, I know I can't take the square root of a negative, so this means I have no real solutions. Okay, so there are no such x values that work. So no solution. Now, for those of you that are curious, I'm going to go ahead and show you what the answer technically is if you get to like an Algebra 2 class. The answer is really negative 0.929 plus or minus 0.923i. And I is equal to the square root of negative 1. It's a so-called imaginary number. So this is a complex solution, not a real one. All right, now here's a little twist. I have to get this into standard form first. So I've got to write this as 6x squared plus 11x minus 35. So I've got an a value of 6, a b value of 11, and a c value of negative 35. So all I got to do is plug it into my quadratic formula. So x is equal to negative b, I'll bring the parentheses back, plus or minus the square root of b squared minus 4ac, and all of this is divided by 2a. Okay, so if I simplify the discriminant inside that square root, I get 961. All right, now, just so happens that I can compute the square root of 961. Okay, when I do that, I believe I get 31. So I really get x equals negative 11 plus or minus 31 over 12. So I've got negative 11 plus 31 over 12, and I've got negative 11 minus 31 over 12. So if I add 31, I get 20. Divide that by 12, so I get 20 twelfths. So this is x equals this, x equals this. Otherwise, I get negative 42 over 12. Now, both of these simplify. I get x equals 5/3 and negative 7/2. Now, I want to show you something interesting about this solution. Okay, and you could have typed these in your calculator. Oops. You could type these in your calculator and get a decimal answer if you'd like. 5/3 is approximately 1.667. Negative 7/2 is exactly negative 3.5. But I'm going to work with these two answers and show you how you could have factored this problem. So the key thing to note is the square root of 961 is an integer value. That means that 961 is a perfect square, which means that I could have actually factored this problem. So let's say I'm stuck. My teacher wants me to factor a problem, but I only remember this quadratic formula that I just showed you. So if I write x equals 5/3 and x equals negative 7/2, I'm going to work backwards to get 0 on the right for both of these equations. So I'm going to multiply both sides by 3 in this first one, so I get 3x equals 5. Second problem, I'm going to multiply both sides by 2, so I get 2x equals -7. Now all I need to do is move those numbers on the right to the other side. So I've got to subtract the 5 to get 0, and I've got to add the 7 to get 0 on the right. So what that means is I could have factored this right here, right, and that should have been equals 0. I could have factored that as 3x minus 5, 2x plus 7 equals 0. And then I know by the zero product property that if I set this equal to 0, I get 5/3. If I set 2x plus 7 equal to 0, I get -7/2. So you can actually use the quadratic formula to help you factor. And that will only work when the discriminant inside the square root is a perfect square. Let's take a look at another one. So we got 16x squared minus 24x, and I've got to add the 9 to the other side. So once I do that, I've got my a is 16, my b is -24, and my c is 9, and it's simply plug and chug. So I get -24 is positive, plus or minus the square root of -24 squared minus 4 times 16 times 9, all over 2 times a, which is 16. So that gives me 32. I end up with 24 plus or minus the square root of 0. My discriminant is 0. And if I simplify this, I end up getting 3/4. So I only get one number because plus or minus 0 has no effect. So when my discriminant is 0, that means I have one solution. When my discriminant is anything bigger than 0, I've got two solutions. And when my discriminant is less than 0, I get no solutions. I get technically complex or imaginary solutions. Now, going back to what I just said about the other problem, if I get x equals 3/4 and I rewrite it to get 0, I end up with 4x minus 3 equals 0. That means that I could have factored this problem right here as 4x minus 3 times 4x minus 3, which is really just 4x minus 3 quantity squared. So we have the same solution twice. This is what's called a repeated solution or a repeated root, and this is something that's common. So I hope you enjoyed. Stick around for the rest of this video if you want to see a little more details. So where did this quadratic formula come from? Well, it comes from completing the square. That's one of the most common techniques in order to find or derive the so-called quadratic formula. And in order to do that, the first thing I'm going to do is subtract c from both sides. So then I get equals -c. Now I'm going to factor out an a. So I'm doing what's called completing the square. I'm factoring out an a, so I have a constant 1x squared, which means I've got to have b divided by a times x. I'm going to leave a blank here, and you'll see why in a moment. I'm going to leave a blank on the other side as well. Okay, so now what I need to do is I need to take half of b over a, and why b over a? B over a is this term right here, the coefficient on x. I take half of that, which gives me b over 2a, and I square that result, which gives me b squared over 4a squared. So I had to square every component inside the parentheses, and I'm going to add that to both sides of the equation. Now, why am I adding it to both sides? Well, if I add it to one side, I've got to add it to the other. But I have to be careful, because technically the left side is being multiplied by this a. So I'm really adding b squared over 4a on the right side, not a squared, because when I distribute the a, one of the a's is gone. Now I'm going to divide both sides by a, so the a on the left is gone, and then I get b squared over 4a squared, which now it kind of looks like what I'd already started with. That's just coincidence, minus c over a. And on the left side, I can actually factor what's inside the parentheses because I'm exploiting what's known as completing the square. So I have x plus b over 2a quantity squared. Where did the b over 2a come from? It was this quantity from the b over a, taking half of it. Now, ultimately I want to find x. But I'm going to clean up the right side first, and in order to do that, I'm going to get common denominators. So I need to multiply this right term, c over a, by a 4a over 4a. So I'm multiplying by 4a over 4a. Okay, and we'll see what that looks like when I clean it up. So I've got x plus b over 2a quantity squared equals b squared minus 4a times c is just 4ac, and then all of this is over 4a squared. Now, in order to get rid of the square root, I square root both sides. So I get x plus b over 2a equals, and when I square root, I technically get a positive or a negative value. So I got b squared minus 4ac all over 4a squared. And if I clean this up a bit more, I'm going to subtract the b over 2a to the other side. So I've got negative b over 2a plus or minus. Now I've got the square root of b squared minus 4ac in the numerator, and then the square root of 4a squared is simply 2a. Now I've got common denominators of 2a, so I've got negative b plus or minus the square root of b squared minus 4ac all over 2a. And that is how you can derive the quadratic formula. Now, remember, some key things to note about applying the quadratic formula. Whenever the determinant, b squared minus 4ac, discriminant, whenever the discriminant is greater than 0, you get two solutions. Whenever it is equal to 0, you get exactly one solution, and it's the same solution twice. It's called a repeated root, repeated solution. Whenever it's less than 0, you get no real solutions. You only get complex solutions. So this is what the three different possibilities are. They're based upon the discriminant, which is what is inside the square root from the quadratic formula. Thank you for watching, and have a great day.